In the next section, we're going to be looking at ellipses. And before we do that, I want to show you how we actually use ellipses in one particular type of construction, and that's in stadium construction. So you're looking at a picture right now of Ben Hill Griffin Stadium on the campus of the University of Florida. And you can see that the sideline is basically a rectangular shape. Now, this does have one advantage in that because it's a rectangular shape, it's going to run right along the sideline, which means that the fans can get incredibly close to the field and therefore incredibly close to the action. But it does have an issue in that because if you're sitting in the end zone along the sideline, then you're going to have to turn your head and you're going to have to look down the row in order to be able to see what's going on if the action's at the other end of the field. So one of the things that we do in stadium building is we actually take ellipses and build our stadiums in the shapes of ellipses. So you can see Bryant-Denny Stadium at Alabama, Jordan-Hare Stadium at Auburn. We've got Williams-Brice Stadium in South Carolina and Vaught-Hemingway Stadium in Oxford, Mississippi, as well as Sanford Stadium in Georgia. And what we see is that the sideline has a curved shape to it. Now, when we rotate the field at Sanford Stadium in Georgia, we can then superimpose an ellipse on top of that stadium. And you can see that that sideline is perfectly in sync with this ellipse. Now, what we do in these American football stadiums is we chop off the end of the ellipse and make it straight so we can, again, get fans as close as we can get them without having a lot of extra wasted space at the edge of the ellipse. Now, the one disadvantage to this, as you can see, is that if you're sitting on the 50-yard line, you're going to be a pretty good ways away from the field just because of the shape of the ellipse. As you get closer to the back of the end zone, the seats get closer and closer and closer. And again, the advantage of this elliptical shape is that no matter where you're sitting, you're going to be pointed somewhat towards the middle of the field and therefore towards the action, which means you're not going to have to crane your neck the entire time while watching the game. We actually got this idea for an elliptically shaped stadium from the Romans. If you think about the Roman Colosseum is actually an elliptical shape, and that's what we're going to take a look at next.
The year was 80 AD, and the Flavian Amphitheater, which we now refer to as the Roman Colosseum, opened its gates. Started under the reign of Emperor Vespasian, the Colosseum was finished when his son Titus became emperor. The seating capacity of the Colosseum was 50,000, an enormous size for the time. Seen from above, the Colosseum is elliptical in shape. It was 188 meters long and 156 meters wide. It was also 50 meters high, or roughly the height of a 12-story building. Part of what held the Colosseum together and allowed for such a grand structure to be built was concrete. The Romans originated the use of concrete, and this substance contributed to the longevity of many Roman buildings. Long before the Colosseum became the center of bloody gladiatorial fights, it was used to reenact famous naval battles from ancient history. The grounds were flooded with water, allowing ships to float and simulate the condition of a battle at sea. Yet of the many battles fought in this stadium throughout the centuries, the very first battle fought on these grounds may have been mathematical. How were the Romans able to build such a large elliptical structure? Why not a circular building? As you have seen, constructing a circle is easy. Take a compass, define a center point, and sweep out a circle. A circle is the locus of points equidistant from a center point. A Roman surveyor, using the surveying tool of the time, the groma, could accurately create a straight line, marking the distance from one point to another. This way, a locus of points defining a circle of whatever size could easily be marked, and a circular structure could be built. This is why circular buildings are relatively easy to create. If we let the surveyor represent the center of the circle, then the surveyor can determine a number of radii, which can be used as the framework for the circular structure. In fact, most circular structures are made up of an embedded regular polygon framework. The vertices of the polygon are what the surveyor mapped out. The ease of creating a circular structure is in stark contrast to the difficulty of creating an elliptical one. The geometry of the ellipse presents some steep challenges. First, the ellipse has 2 points that are the equivalent to the circle's center. These 2 points are called the foci. The ellipse is the locus of points such that the sum of the distances from the foci to the ellipse is a constant. Here is one way to construct an ellipse. Take a loop of string, 2 thumbtacks, a pencil, and a sheet of paper. Tack the paper on a bulletin board or similar surface with the 2 thumbtacks. These tacks represent the foci of the ellipse you are about to construct. Place the loop of string around the tacks. Take the pencil and extend the string so that you end up with a triangular shape as shown. These 2 sides of the triangle represent the distances to the foci from the vertex of the triangle. This vertex is a point on the ellipse. Keep the string taut and move the pencil to different locations, in the process constructing the ellipse. As you move the pencil around, the side lengths of the triangle change, but the total amount of string that represents both sides is constant. In other words, the sum of the lengths of the 2 sides of the triangle is constant, fulfilling the requirement of an ellipse. Constructing an ellipse this way is straightforward, but transferring that technique to the world of surveying and the construction of buildings, especially during the time of the Romans, is a challenge. The simple situation of one surveyor defining a number of radii becomes 2 surveyors whose measurements must align at a 3rd point, and the sum of their separate measurements must be a constant. Furthermore, this 3rd point, the one on the ellipse, is constantly changing its location and changing the 2 side lengths of the triangle. This would have been very difficult to achieve without resulting in an inaccurate curve. Furthermore, constructing architectural plans or blueprints for an elliptical structure would have been impossible, since there's no way to construct an ellipse using a compass and a straight edge. So why did the Romans build an elliptical stadium? And how did they do it? The first question is easy to answer. Since an ellipse is a wider version of a circle, then the larger area would result in more available stadium seats. For example, here is a circle of radius r, and here is an ellipse of width 2r and length 4r. The area of the circle is pi r squared, while the area of the ellipse is 2 pi r squared, twice the area of the circle. The perimeter of the ellipse, on the other hand, is only 50% longer than that of the circle. This means that the cost of materials to build an elliptical structure of twice the area of the circle is not twice the cost. So there's an economical reason for building an elliptical structure. The answer to the second question, how did they do it, is more difficult to answer. Because of the condition of the Colosseum, it makes it difficult to make a final determination about how it was built. There is evidence to suggest that the Romans used circular arcs to approximate the shape of an ellipse. Let's analyze how this would work. Here is an ellipse proportional to the arena portion of the Colosseum. It is possible to overlay a series of circles, so that portions of each circle overlaps the curve of the ellipse. For now, we will look at just the portion of the curve in the XY coordinate system's quadrant 1. Piecing together the 3 arcs shown reveals a curve remarkably close to that of the ellipse. Since this ellipse-like shape is actually made up of circles, then once again the engineering challenges are no different than for a circular structure. This would have eliminated the insurmountable obstacle to building the Colosseum. Let's use the TI Inspire to explore this construction.
So let's say that you wanted to draw a perfect circle. There's an easy way of doing it. You could take a pen and a piece of string, and you can put the pen, in this case, in the corkboard, or if we were trying to draw it on wood or cut out wood, what we would do is we would take a nail or screw and put it into the wood, And then what we're going to do is we're going to take the string and we're going to put it on there, right there, to our desired length. So we would have a radius here. Then what you would do is you would just take like a pen and you would draw around it just like this until you got all the way around and you created your circle. Well, ellipses, we do have a center of an ellipse, but we don't have infinite axes of symmetry with an ellipse. So what we would do to draw a nice perfect ellipse is this. Instead of just one, we're going to take one pen and then a second pen, and these are going to be the foci of our ellipse. And what we're going to do is we're going to put our string on just like that. Now what happens is when I pull this tight, you can see that no matter what, the distance here is always going to be the same between the foci. And if I take this length of this side of the triangle and the length of this side of the triangle and I add them together, they're always going to be the same no matter where they are. So what this means is I can take a pen, just like I did with the circle, and I can go all the way around just like this, and then eventually I'm going to get to the bottom side, but it's going to continue on, and I can draw a perfect ellipse just like that with a piece of string and two pens. So when we look at the Roman Colosseum and how they built that or how they planned that out, this is how they would have done it. For this next section, we're going to look at ellipses. Now, ellipses can either be horizontal or vertical, depending on the equation that you're given. There are a lot of terms that we need to go over with ellipses. So let's look at a horizontal ellipse first. The equation for a horizontal ellipse is going to be x squared over a squared plus y squared over b squared is equal to 1, where a is greater than b is greater than 0. I'm going to come back to this in just a couple minutes when we go over vertical ellipses, so you can see the difference between the two and be able to identify which one is which very, very easily. So going to all of our terms that we've got with an ellipse. First, this is the ellipse right here in pink. Then the center of the ellipse is identified in green. Now the ones that we're going to work with, the center is going to be at 0, 0, and that's basically all we're going to do in this class. Then you've got two axes that we're going to identify that are running through the ellipse. And so the first axis is the major axis. And the major axis is going to be the one that basically runs the length, or it's going to be the longer of the two axes. The minor axis in a horizontal ellipse is going to run vertically. Now, the minor axis is going to be the one that is smaller or shorter. Then the other thing that you would want to know about the major axis is that the major axis is going to run through each of the foci, or each focus. Now we'll talk about what the focus means for an ellipse in just a little bit as well when I show you how to draw an ellipse, or at least draw a perfect ellipse. Then the next big thing that we need to look at is the vertex. The vertex is going to be located on the major axis. Then you also have a co-vertex, or two of them, which are going to be located on the minor axis. Now, when we do this as a vertical ellipse, we basically just flip everything. So, since the co-vertices were on the y-axis this time over here on the vertical ellipse, they'll be on the x-axis. The vertices were on the x-axis on the horizontal ellipse. On the vertical ellipse, they'll be on the y-axis. Now, the vertices, the co-vertices and the foci are all going to have specific points. The vertex points on a horizontal ellipse are going to be at plus and minus a and then 0. So you can see that you're going to move along the x-axis and you're not going to move up or down any as long as our origin is 0, 0. The co-vertices are going to be located at 0, plus or minus b. So we're not going to move left or right any. Instead, we're only going to move up and down. Then our foci, or the two focuses, will be at plus or minus c and 0. And they're going to be located inside of the ellipse. When we go over here to the vertical, you can see that all we do is we switch their spots. So the vertex becomes 0 plus or minus A, the co-vertex becomes plus or minus B0, and the focus becomes 0 plus or minus C. Now, going back to these equations, the reason why they're important to know, with the horizontal ellipse, you're going to have x squared over a squared plus y squared over b squared, where again, a is greater than b is greater than 0. So for a horizontal ellipse, the bigger denominator is going to end up over here. Okay? So your first denominator is always going to be the bigger denominator whenever we're dealing with a horizontal ellipse. Over here on the vertical ellipse, we still have the same rule in place. A is greater than B is greater than 0, but this time the A value is over here underneath y squared. So whenever you have a vertical ellipse, your larger A value is always going to be the second denominator, or the larger value would be in the second denominator if it's going to be a vertical ellipse. And so that's an easy way of trying to keep them straight as to whether you're going to have a horizontal or a vertical ellipse. For problem number 1, we're going to find the equation of an ellipse that has its vertex at -6, 0 and its co-vertex at 0, 3. So just to figure out which equation we want to use, whether we're going to use the equation for a horizontal ellipse or an equation for a vertical ellipse, what I'm going to do is I'm going to come over here. I'm actually going to plot these points real quick. So I know that I've got a vertex at -6, 0, so it's going to be here, and then we would also have another vertex over here at 6, 0. The co-vertex would be at 0, 3, so it would be there and there. So you can see that I've got a longer ellipse than I do a tall ellipse. So that tells me that I'm going to be using the formula for a horizontal ellipse, which is going to be x squared over a squared plus y squared over b squared equals 1. Now it's pretty simple from here on out. Since I know that the vertex is the a value, I'm just going to plug that in for a. So this becomes x squared over -6 squared plus y squared over b squared, which is 3. And that's set equal to 1. X squared over 36 plus y squared over 9 equals 1. And that right there is how you're going to find the equation for a horizontal ellipse given both its vertex and its co-vertex. Now let's say that we were given an ellipse with a co-vertex and the knowledge that the center of the ellipse is at 0, 0. How would we find the focus with that information? Well, what we want to do is we want to take a look at the ellipse itself. So we know that the center is at 0, 0, and we know that the focus is going to be plus or minus C0. So what I've done here is I've marked the focus 2 at C0. What that means, because the origin is the center, that means that the distance between the center and focus 2 is going to be C units. So what I've done is I've marked that as C on here. Then if we look at the co-vertex is going to be at 0 and then plus or minus B. I'm going to look at just the top co-vertex here. So that's at 0B. Since again, the center is at 0, 0 and the co-vertex is at 0B, that means that there's B units in between 0, 0 and 0B. So the length of that particular segment is B units. Okay? Now what we can do is we can then use the Pythagorean theorem to try and figure out what is the value of C. So we're going to take this right here and we're going to draw in a hypotenuse, and now we've got a 90-degree angle. So what we want to do is we're going to call this A right here. We're actually going to modify the Pythagorean theorem a little bit. Normally we would say a squared plus b squared equals c squared. Now what we're going to say is a squared, because a is the hypotenuse, is equal to b squared plus c squared. And you're going to see how we use this in the next problem. Now we're going to apply what we just learned. So in problem number 2, we're given the equation 25x squared plus 9y squared equals 225. And we're asked to find what are the foci of this particular ellipse. But to be able to do this, we need to put this into standard form. So we're going to go ahead and divide everything on here by 225. And remember, the reason that we're doing this is because we want the number that's over here by itself to become 1. Now, what you'll notice is that 25 times 9 is 225. So really what we're doing is we're just reducing this down, and we're going to be switching these numbers. So we're going to get x squared over 9 plus y squared over 25 is equal to 1. Now, one of the things that you want to remember here is that whichever denominator has the larger number is going to tell you whether you've got a horizontal or a vertical ellipse. In this case, since the larger number is in the second denominator, that's telling us that we're going to have a vertical ellipse. So this is b squared and this is a squared. So when I do b squared equals 9, I'm going to get b is equal to plus or minus 3. When I do a squared is equal to 25, I'm going to get a is equal to plus or minus 5. So I'm going to come over here and I'm going to graph 3 and negative 3 for b, and I'm going to graph 5 and negative 5 for a. And then I'm just going to sketch in this ellipse real quick just so I can see what I'm working with. And I know that the focus has to be somewhere along that major axis inside of the ellipse. So now it's just a question of what do we do to find that? Well, remember that we're working with Pythagorean theorem here. So we've got a is 5, and we're going to do a squared is equal to b squared plus c squared. So it's, instead of doing c squared is equal to a squared plus b squared, which we normally do. So we're going to get 5 squared is equal to 3 squared plus c squared. So it's going to become 25 is equal to 9 plus c squared. And so c squared is going to be equal to 16. And so c is going to be equal to plus or minus 4. So I know that the foci of this are going to be at positive 4 and negative 4. And that's how you're going to do this.